SwayamPrabha. Digital India. Educated India.
So, last time when we ended, we were discussing about the angle at the critical point, whether we are looking for the question what happens to the angle at the critical point of transformation. At all the regular points we have seen or established that the angle is preserved, the angle at the z plane and angle at the zeta plane are same, the points where the transformation is regular. At the critical point of the transformation, we are looking to see what happens to the angle. So, what we find that at the critical point of transformation, the transformation being this is the transformation and this is the critical point, and we have seen that we can expand this function near the critical point as where zeta 0 is, okay, we will write it. What did we write? 1 plus did you write b n or some other coefficient here? A n b 1, okay. Where this zeta 0 is zeta at z 0. So, it is a constant and we assumed okay. This is what we assumed. The point is z 0 is a critical point, meaning that the first derivative is 0, and in addition we assume that all the derivatives second, third, fourth up to n minus 1 all are 0. Okay. Let us assume. Then this part of this function, this part of the function, let us call that another function, okay. This part of this function 1 plus b 1 z b 2 z square and this we are denoting by f z. Okay. Now, this f z is of course again analytic, and it has no critical point, because you have already assumed that up to n minus 1th derivatives are 0 and nth derivative and others they are non-zero. Nth derivative is non-zero, that is what we have assumed. So, the nth derivative is basically the first derivative for this function now, hence that is not 0. So, this part of this function is not, I mean z 0 is not a critical point for this. So, we will write f z is analytic. However, z 0 is a critical point for the transformation zeta. That means that criticality comes because of this part. Okay. So, we can say that this implies that comes through now we can look to the angle that it happens. Now, once again that argument of the left hand side is sum of the argument on the right hand side. So, if we now consider two curves that are intersecting at point z naught in the z plane and at point zeta naught in the zeta plane, then the angle between two curves z naught in the z plane and that is zeta naught in the zeta plane. This is to be interpreted in that way, that in one plane it is intersecting at z naught, in the other plane it is intersecting at zeta naught. Curve 2 minus curve 1 Now, f z is a conformal transformation. So, this angle is, this part is 0, okay. This part is 0. So, what we see that in this case the angle has become n times. What is n? The first derivative which is non-zero. N is of course an arbitrary, depending upon the function that we are choosing. That is what is n. So, you have to just find out what is the lowest order of derivative that is non-zero at the critical point. Critical point means the first derivative is 0, then we seek whether the second derivative is non-zero, third derivative is non-zero and so on. Only we need the lowest. We will find out in some cases what will happen to the angle. Now, before we try to apply this transformation, as we said that our plan or our aim is to apply this transformation so that an airfoil becomes a circle. We would like to apply the transformation in such a way that an airfoil becomes a circle or vice versa, circle becomes an airfoil, because we are interested in flow over an airfoil. However, before we apply that transformation or look for some sort of transformation, let us consider, since we have to consider everything in complex plane, let us look for the potentials, the complex potentials first of all. So, what are the complex potentials? So, we have seen that our basic flows or the basic solutions of Laplace equation are a uniform source, uniform flow, point source, point doublet, point vortex. So, what are the complex potential for these basic flows? Let us say what is the complex potential for our uniform flow or uniform system. Yes, uniform stream, let us say in the x direction. We will write some of these complex potentials. Complex potential for basic flows. Uniform stream in the x direction is uniform stream in x direction. What will be the complex potential? Yes, complex potential we denoted by F, no, capital F. Okay. What is complex potential? Phi plus I psi. For a uniform stream in x direction, what is phi? Uniform stream in x direction, the magnitude of the flow velocity is u infinity. Okay. So, what is the complex potential in the z plane? Yes. Phi plus I psi. What is phi for a uniform stream in x direction? U infinity x. Psi? U infinity y. So, what is complex potential? U infinity x plus I u infinity y. What it is? U infinity z. Let us say the undisturbed stream is such that it has two component y, u infinity and v infinity. Uniform stream, but it is not along x axis. It has two component, one along x, one along y, and the components are u infinity and v infinity. Components are u infinity, v infinity. Then what it will be? Just go on adding. U infinity x plus v infinity y okay. And we want it to be expressed in terms of z, not x and y, no longer x and y, that will not help us. See, for the u infinity component, again this f z will be u infinity z only. So, find what is for v infinity and then add it, that would be here. I z bar. I z bar can't be expressed in terms of z. Is it this? Is it this? All right. Okay. Let us say the same velocity, but instead of expressing it in terms of component u infinity v infinity, we say that the uniform stream is at an angle alpha. You know, that is rather perhaps more dear to us, at an angle of attack, the flow at an angle of attack. So, let us say that uniform stream, the magnitude is, let us say q infinity and angle alpha. q infinity at an angle alpha, alpha to the x axis, angle alpha to the x axis. So, what will be f z? For the x component of the velocity q infinity cos alpha, phi is q infinity cos alpha x. Okay. So, let us write q infinity x cos alpha for the y component, it is q infinity y sin alpha plus I psi. Psi is what? For the x component, minus or plus? For the x component, say plus I q infinity y sin alpha or u infinity y cos alpha. Okay. And for this one, minus I q infinity x sin alpha. Then what do we get again? This and this together make q infinity cos alpha z. These two together q infinity cos alpha z. Or let us say q infinity z cos alpha, and these two minus I minus q infinity z sin alpha. I is there. Is this all right? Is this all right? So, q infinity z cos alpha minus I sin alpha, what is that? What it is? Cos alpha minus I sin alpha is e to the power minus I alpha. Okay. So, what is, say, the positive angle of attack alpha, that is this, if this is the x axis and this is the angle alpha, which we call the positive angle of attack, then it is multiplied by e to the power minus I alpha. Of course, in complex notation, all the rotations are expressed by e to the power I theta. Let us now consider this a uniform, say a point source placed at point z naught. Instead of origin, we are placing the point source at z naught. What will be the complex potential? Point source placed at z naught. For point source, what we have denoted as strength of the point source, m or sigma. What did you use earlier? We will use the same m, I think, m. Okay. So, we will use m. So, point source placed at z naught, what will be the complex potential f z? Let us say forget about z naught, think about origin, point source placed at origin. Then what is the complex potential? Phi due to a point source is 2 dimensional point source, that is infinite line source. By point source I mean now infinite line source. See, we are in this complex, as long as we are dealing with complex means it is only 2 dimensional flow, because it is not 3 dimensional flow. Complex numbers are tuples. So, we can use it only in 2 dimension. M by 2 pi log r, okay, is the, and that r is the distance from of the point from the point source. So, if the point source is at other location, then it will be r minus something. Okay. See, if the point source is located at x naught, then it is r minus x naught, and so on. And what is the stream function for point source? M by 2 pi theta. So, m by 2 pi log r plus I theta. So, what is that? Log of r e to the power I theta, that is log of z. If the point source is placed at z naught, it will simply become log z minus z naught. So, it is m by 2 pi log z minus z naught. A doublet, source doublet, again located at point z naught. And let us say that doublet axis is along x axis. A doublet has axis, I think we mentioned earlier, it is the line joining source to sink, or sink to source, that is called the doublet axis. The direction is from sink to source, but the line joining source and sink, that is called the doublet axis. Okay. In a doublet, the source and sink are infinitesimally distance away, the separation between them is 0, approaching 0, but they may approach 0 along x axis or along y axis or along some other line. So, we will consider doublet which has axis along x axis, the doublet which we considered earlier, the doublet which was required for flow past a circular cylinder, which has a doublet axis along the x axis, that is both source and sink are placed on the x axis itself. So, point doublet with axis along x and located at z naught. You remember it was minus mu by 2 pi cos theta by r. The potential was minus mu by 2 pi cos theta by r. So, what will be the complex potential? Complex potential. At that phi and psi, that phi and psi you have already written many times. The phi is minus mu by 2 pi cos theta by r. When it is located at origin. So, it will become minus mu by 2 pi when we add phi and psi minus mu by 2 pi e to the power minus I theta by r, or r e to the power I theta, which is z. So, minus mu by 2 pi z located at z 0, z minus z naught. So, this is a clockwise point vortex located at z naught is what it is. The potential function is minus gamma by 2 pi theta, and the stream function is gamma by 2 pi log r. So, what is the complex potential? Minus I gamma by 2 pi log z minus z naught. Now, let us say any flow that can be represented by potentials, either real potential or complex potential. Can you say what will be the general form of that complex potential function? Any flow. Let us say the flow is such that it can be represented by a potential function. So, it is a for any flow the complex potential, let us say a function f z, okay, and any function can be represented by an infinite series. Yes. Then what will be the general form of that series in this case for a flow problem? A general function is of course a n z, a general series or polynomial is say a n z to the power n, where n changes from minus infinity to plus infinity. Okay. Now, can this be used to represent a flow problem? See, flow which is caused by some body moving through the fluid must be such that at far away, that is at infinity, there will be no effect of the body, yes, which is infinity boundary condition, that a flow which has been created by the motion of a body through a fluid at rest, say, then at far away the effect of the body will not be felt. The fluid at infinity will not feel that there is a body moving through it. If that is so, what is the highest positive power for n possible in that expression a n z to the power n, n approaching minus infinity to plus infinity? The complex potential is represented by a n z to the power n in general case, where n changing from minus infinity to plus infinity. But is it possible for a flow problem to have such a complex potential where a changing from minus infinity to plus infinity? No. Minus infinity is possible, but plus infinity is not possible. We cannot have n more than 1, because n more than 1 means we have say n is 2, means we have a 2 z 2, a 2 z square complex potential. Then what will be the velocity, complex velocity? That will contain a 2 z, some constant into z. And what does it mean? As we go away, velocity is increasing. If the velocity contains an linear term in x, means as we go away the velocity increases. That means, when a body moves through a fluid, its effects will increase as the distance is increased, which is of course not practical, absurd. So, in the expression for velocity, there cannot be any x or z term. Okay. So, in the complex potential, there cannot be any z square or higher order term. This is not possible. Okay. So, the most most general complex velocity potential for a flow problem, you can write So, the most general is a complex potential the constant term that is z to the power 0, that we are not writing, because in the complex, as long as potential there is a adding a constant does not make any difference. And looking to our basic solutions, we can see that this A 0 z, this part of the potential must be due to the uniform stream. That uniform stream has a potential which is proportional to z. Okay. Of course, so I forgot one more term, that log term should have been written, but log or log term we put it here, and we will make that as a 1 log z, and then we will make it a 2, a 3, let us say, and so on. Is that what I did? And the complex velocity, will come as a constant term which represent the uniform velocity plus or sorry just to make a difference, let us say change the coefficients from, or let us say first write it in this way, then of course, we should write here minus, okay, and so on, and just to avoid all those, you will write it in this way, B 0 plus B 1 by z plus B 2 by z square Okay, let us now consider what will be the force that will act on a body, the force exerted on a body by the flow. So, what are the forces? We have already discussed this. The force, the lift and drag force, or the x and y force. The x component of the force, the force is only because of pressure. Let us consider a body, any arbitrary body. Okay. Y, and the pressure is acting normal to this body. Okay. The pressure is always normal to the body. The flow direction can be taken to be like this, q infinity, and this angle is alpha. What is the x component of the force? The x component of the force is, we wrote this formula earlier, minus p minus p infinity cos theta, if we consider a small length of ds, arc length of ds integrated over the entire curve. Okay, theta equal to 0 to 2 pi. Agreed? And similarly, the y component of the force is you can replace p minus p infinity by the appropriate Bernoulli's equation, or you can make p infinity, that the contribution due to p infinity will be 0, or integration over this closed curve of p infinity cos theta is 0, p infinity sin theta is also 0. So, this expression even can be written as simply p cos theta. From there also you can make it. You can replace p by equivalent Bernoulli's equation. What do you get then? Let us say at this point the flow velocity is q, then according to Bernoulli's equation, p infinity plus half q or rho q infinity square equal to p plus half rho q square. So, what will be p minus p infinity? Yes, half rho q infinity square minus q square. Okay. Out of the this q infinity square is again a constant, So, when it is integrated over this closed curve, again its contribution will be 0. Okay. So, what in effect will remain as half rho q square. Then can we write x plus I y, what it is? Write x plus I y. What is x plus I y? What is x plus I y? Or perhaps it will be more convenient to write x minus I y, instead of writing x plus I y, write x minus I y. Write x minus I y. This will come as minus rho by 2 q square e to the power minus I theta ds. Okay. X minus I y. Got it? Now, what is complex velocity? The complex velocity W, as we know earlier, W equal to, the complex velocity W is u minus I v, means q e to the power minus I theta. Okay. The complex velocity W is q e to the power minus I theta. So, if we substitute it here, what do we get? X minus I y equal to minus rho by 2 W square e to the power I theta ds. And what is e to the power I theta ds? What is e to the power I theta ds? 0. E to the power I theta ds. E to the power I theta ds. ds is what? An incremental length, arc length, and e to the power I theta, it simply transforms it, rotates it. How can it be 0? If you rotate a length, it cannot become a 0. It become perhaps a different length. You have a length like this, you rotate it, it becomes this length. You have a arc length like this, you rotate it. It simply perhaps changes its direction and might be magnitude also. In this case, of course, e to the power I theta. So, there is no question of changing total magnitude, it cannot. So, what it will become? E to the power I theta ds. Can you relate it with dz? dz is what? dz is dx plus I dy, and dx and dy, can you relate it with ds? What? dz is, let us say dz is dx plus I dy, okay. And ds is e to the power I theta ds. Cos theta ds plus I sin theta ds. What it is? dz? Look to your an arc length in that figure and then see what will be dx dy. It is not just arbitrary. Consider a ds length ds and then see what it is. Let us say we are, we will continue with, let us see. বলে দাও, তারপর স্টার্ট করতে।